everyone, thanks for joining us today and welcome to Steam Management's webinar series. In today's session, we'll be discussing the process of retrofitting conventional hydronic heating systems with condensing boilers. Our host today is Chase Bean, Steam Management's Vice President of Revenue and Engineering. Chase is a professional engineer in multiple states and has over 16 years of experience in engineering, project management, and business development in the energy sector. I'll be monitoring the chat, so feel free to ask questions at any time during the presentation, and we'll answer as we go. I'm also going to launch a few polls, so look out for those too. And thanks again for tuning in, and I'll let Chase get started.
All right, thanks, Ashley, and thank you everybody for joining us. We are Steam Management. We provide turnkey retrofit projects with a focus on efficiency improvement, particularly in steam systems, but we work in other utility systems as well. Our solutions reduce energy system energy costs, conserve water, and reduce carbon footprint. We serve a variety of markets, basically anyone that has steam. There's something that we can do for you. This is me. My email address is there, and our typical process for doing the PDH certificates is to email me once you've completed the webinar, request a certificate, and I'll send that back to you. As always, you can view our past webinars at steammgt.com/webinars, and this one will be available as well once we've finished the webinar. Here's my disclaimer for the presentation. The presentation is intended for technical and educational purposes only. It is designed to provide general information about condensing boiler technologies, their applications, and their operational principles. We are not affiliated with or representing any specific equipment manufacturer, distributor, or product line. The inclusion of any specific products or features is solely to illustrate concepts and should not be interpreted as an endorsement or promotion. Attendees are encouraged to conduct their own research and consult with SMI when selecting equipment to meet their specific needs. Okay, so today's overview, we're going to talk about the basics of hydronic heating, the basics of condensing boilers, some system configurations, and your considerations for retrofitting if you're considering condensing boilers. So basics of hydronic heating. I'll say that for hydronic heating, we're talking about a hot water heating system or a glycol and hot water mixture in the heating system, not steam. Condensing boilers are for hydronic heating systems only, not steam replacements. If anybody mentions condensing boiler in the context of steam, they're talking about maybe a condensing economizer or something like that. And we'll talk about why that is later. So this is the concept of hydronic heating. Pretty simple. You have a boiler, you're circulating, you're heating hot water, you're circulating that water through heat emitters. It can be a variety of different types of emitters or terminal units. Here we're just showing baseboard fin tubes. And then those emitters emit heat to the heated space and then return colder water back to the boiler. And it's heated again, and the cycle continues. So pretty simple. Key components here, you're going to have a boiler or a heat source. That can be a hot water boiler, an old conventional boiler, or a condensing style hot water boiler. You could have a steam boiler with a hot water conversion, which is basically just a heat exchanger, taking heat from the steam, turning that into hot water. You can have heat pumps heating the water, electric boilers, solar heating, geothermal. And in many cases, some of these sources can just supplement the energy supply and not be the sole provider, but it's a very flexible system. Terminal units, there's a variety of terminal units. I won't read all of these, but generally you're either having some sort of heat exchange surface area where the air is naturally flowing over it to extract the heat, or you have a fan blowing over the coil to promote that heat transfer and then blowing the air out into the space. So that's what we're talking about. We're talking about terminal units, all these different things that are using the hot water from the system. You have circulation pumps. Those can be primary, secondary, or tertiary pumps. We'll talk about more specifically about those later. You have a decoupler, which is applies to primary, secondary systems. So you don't always have that, but we'll talk about that later as well. Control valves and instrumentation. You can have water filters, and they're recommended. You can have a full system water filter where it takes the full flow of the system, or you can have like a slipstream filter where maybe it takes 10% of the flow and kind of filters the water over time. You have an air separator to remove air from the system. That's very important. Air in a hot water system promotes corrosion and reduces the life of components. You have expansion tanks to allow fluid expansion as it heats and cools. And then you have a buffer tank to add volume to the system and give you some thermal inertia, which we'll talk about later. I should mention too that air separators should be installed where the system is the warmest and the pressure is the lowest. So those are the locations where the gases are encouraged to come out of entrainment from the fluid, and then they can be rejected with the air vent on the air separator. Here's a bunch of this table is really more for reference after. I'm not going to go through everything here, but some points as to, comparing hydronic heating to other heating systems. It's similar to steam, although I would say that people really endorse the comfort of steam heating, and we're obviously big fans of steam heating. But hydronic heating can be a little bit more flexible. As compared to heat pumps, it's going to be better in extreme cold, and also can easily be integrated with renewable energy sources, as I mentioned before, like solar heating or geothermal heating. So a lot of times a hybrid system might be something to consider if you're really wanting to integrate those heat pumps, but you're worried about meeting capacity in the dead of winter when they don't perform as well. Maybe you consider having a hybrid system. Okay, we're going to go in the basics of condensing boilers. I think Ashley has a poll for you.
Yeah, I just launched our first poll before we get into this section, which is, have you worked on installing condensing boilers in your facilities or projects?
Okay, great. We got a lot of people familiar with condensing boilers, so that's good. So here's the concept. So this is a conventional boiler for comparison. You have a burner taking air and fuel in, firing across a heat exchange surface, and those flue gases give up sensible heat to your hot water. Typically, traditionally, hot water systems are designed to a set point of about 180 degrees with a 160-degree return. And so this is all sensible heat. Your flue gas exits the boiler. It's still, everything's still vapor, and 300-degree outlet temperature is this can vary, but that's a reasonable outlet temperature. Generally, for a newer conventional boiler, you're going to have efficiencies at 80 to 87%. If you're retrofitting, your boiler could be degraded over time. The heat exchange surfaces could be fouled up. Your burner controls could be out of whack. I mean, you could be operating at much lower efficiencies. So putting in a newer advanced control boiler, such as a condensing boiler, should be a significant efficiency gain. So this is the condensing boiler concept. So instead of, let's just say we're taking combustion air and fuel in, we're going across the coil, and you're getting that initial sensible heat similar to the conventional boiler, but you have some excess surface area here, which is taking that flue gas temperature down further to the point at which the water in the flue gas starts condensing and dropping out of the flue gas, and you're getting that additional latent heat as well. And you can get really low flue gas outlet temperatures here. That condition is purposely avoided in conventional boilers because they are not made out of materials that can withstand the acids that drop out of the flue gas. And so the difference here is that with more advanced materials on your heat exchange coils, they are resistant to those acids, and you can condense in your flue gas, and it's not going to corrode the boiler. That is an active process. So when this is in condensing mode, you are consistently dropping water out of the flue gas, So that water is being drained out, and it has to be neutralized before it's sent to drain. In condensing mode, what I'm calling conducive conditions, you can get a 90 to 98% efficiency. Otherwise, you're going to get, 87 to 90% efficiency is basically an advanced conventional boiler. If you're not in condensing mode, you're basically turning your condensing boiler into a conventional boiler and not getting that extra efficiency. And we'll talk more about that. This is a second view, and the takeaway here, it's the same concept. This is more of like a wall-mounted instant hot water heater kind of configuration. But what I wanted to point out on this, this is from the Department of Energy, a diagram they had. And what I wanted to point out here is that there's often a secondary heat exchanger. So you have your primary heat exchanger, which is basically your conventional style heat transfer, and then your secondary heat exchanger where you start getting your condensate coming out of your flue gas. So this is a generic condensing boiler efficiency curve. So on your y-axis here, you have your boiler efficiency. On your x-axis, you have your hot water return temperature. So this return temperature is what's going to drive whether or not your boiler can get into condensing mode. The different lines are different loads. So the boiler's efficiency at 25%, 50%, etc., at each of these hot water return temperatures. So the takeaway here is you have to get that hot water return temperature down below 130, 135 to really get into condensing mode, and then you'll quickly increase your efficiency of your boiler. So if you have a traditional or hot water system and you actually have a set point requirement of 180 degrees at all times, your return temperature is probably not going to get down to where you can get into condensing mode, and you're not going to get the benefit out of that boiler. So we'll talk more about how to optimize that later. This is one way, and this is kind of the most common way I would say to retrofit is to make sure that you're using an outdoor reset controller. And the idea here is that your set point of your supply temperature to your system modulates based on your outdoor air temperature. So you can see at 0 degrees on the x-axis, this is outdoor air temperature. On your y-axis is water temperature. The blue line here is your supply temperature. So what your supply is set to, we're assuming a 20-degree delta T. And so this is your return temperature, this light blue line. And so at 0 degrees outdoor air temperature, let's say you need that full 180-degree set point like you've always been operating at to get the appropriate heat. You're not in condensing mode, but as the air temperature warms up, eventually you continue to reduce your supply temperature set point to a point where that return temperature starts crossing this green condensing line threshold. And then for these outdoor air temperatures, you're in condensing mode and you're getting your mid 90 efficiency operating points. This is a plot of heating degree days in New York City. And so when you're really going to get this condensing mode is on these shoulder months where you have a little bit milder temperatures. You can reduce that set point and get the full efficiency out of the boiler. System configuration. So I'm going to go over some of the more common hydronic system configurations, just kind of a high level overview. And then later on, we'll talk about how these apply with the condensing boiler retrofits. So this is what's called a flow through configuration. This is one of the more simple configurations. You have your boiler, your pumps coming out or circulating water out of it. And basically all of your users are in series. So you're flowing through all of your users. There's no parallel flow pass. It just goes through all the users and comes back. This is actually a pretty good scenario for a condensing boiler because you are minimizing that return water temperature coming back to the boiler. But this is not very common for any applications that have different zones. You're going to see this in small residential applications, maybe if it's a big storage room like a warehouse or something like that. But if you have any sort of zoning or zone requirements, this is not going to be a good application. This is called direct return. So now we're getting into some simple zones where you have balancing valves that promote the flow through each zone that you want. The disadvantage here is that you really rely on these balancing valves to force flow through to your more remote users. So that's kind of the downside. So this is for simple zoning applications, maybe medium-sized buildings, commercial buildings. And this is also known as two-pipe direct return, so you'll hear that sometimes. So this is reverse return. You're getting a little bit more, a little bit better design than the direct return. Basically, it's the same idea, but your return line is coming from your more remote unit or emitters. And the downside here is you got a little bit more piping. But on the plus side, you're relying a little bit less on your balancing valves because it's more naturally balanced through the system. And so you should have a little bit less pumping energy because you're not having to throttle that flow so much. This is a variable flow primary system. So basically kind of the same idea, but your primary pumps are on VFDs and you pump out to the system back through the boiler. So your system pumps are also your primary pumps that pump through the boiler. This is a recommended configuration for new condensing boiler installations, which we'll talk about later. The advantages here, you have less pumps than the primary secondary system, which is we'll talk about next. So it's a little bit easier on maintenance and things like that. Lower installed cost, lowest pump energy. And also one of the reasons it's recommended for condensing boilers is it ensures this minimum return temperature because there's no blending of that return line. Alternatively, you can have a primary secondary system. And the idea here is you have this primary loop that circulates. In the past, this has often been a constant loop. So you have a constant flow through this, and then you pull off of this with your secondary pumps to pump out to your users. And so you have a secondary loop. And basically, you're always going to want to overpump your primary loop as compared to your secondary loop. And so you'll get some flow back through this orange line. This is called your decoupler, which can be, the decoupler can be piping, it can be a buffer tank, it can be they actually have products that are just decouplers to kind of install in that location. And that's the idea here. So we'll go through how this applies to condensing boilers more in a minute. Also, I should point out there can be a different combination of VFDs on this pump. So you can have a primary, secondary variable, which is where your primary pumps are constant. Secondary pumps are on variable speed. You can have primary variable, secondary variable, where everything's on VFDs. It depends. So there's a lot of different sub configurations off of these. I should also mention that off of these secondary loops, you can have tertiary loops. So you could have a whole different loop where this can get pretty complicated if you have a lot of different zones. You can have a lot of different loops coming off of these loops. Back to the decoupler, though, this is the concept of the decoupler. So again, we're talking about this orange loop here, so or orange path. If you have equal flow in your primary and secondary loops, basically your primary is going straight to your secondary is flowing right back into the return of your boilers, and you have no decoupler flow. So you would be going through this out of the boilers, straight from primary to secondary, all the way around back straight into the boilers, and no flow here. That's ideal, right? That's not real world scenario most of the time. Most of the time you're going to have at least some flow, primary flow that's exceeds your secondary flow. And in that case, you're going to return some water back to your return, or you're going to supply some hot water back to your return water, and you're going to get some blending and increase that temperature. And again, that's why this scenario is not ideal for condensing, because you're heating up your return temperature a little bit, and that's going to not promote being in condensing mode. The last scenario is if your secondary pump is out pumping your primary loop, and that's a situation you want to avoid, because if your secondary loop is out pumping your primary loop, you are mixing cold water in with your intended hot water that's supposed to be going out to the system, and you're not hitting your supply temperature, and can cause control problems, nuisance trips, and obviously reduce comfort levels in your system because it's not operating as intended. Ashley's got another poll for you guys.
Yeah, this poll is asking if you've retrofitted hydronic heating systems. Have you also reconfigured the primary and secondary pump system as part of the project?
Give you guys a second for that. That's an interesting question, because it is something to consider. We'll talk about in a minute. Which leads us to considerations for retrofitting. So there's a lot of things to think about here. Retrofitting with condensing boilers is different than doing a new installation, and we'll talk about that here. So why would you retrofit with condensing boilers? Obviously, you're looking for higher efficiency ratings in your conventional hot water boiler. You want to lower your operating cost. You want to decrease your carbon footprint. There are utilities incentives available for these units. They give you tighter temperature control than your older boilers, although advanced control on a new conventional boiler would be probably similar. They have a smaller footprint. They're sort of modular, so you can scale your capacity. And oftentimes when you're retrofitting, because they have a smaller footprint, it kind of leaves room for additional boilers. And you can go with N+1 redundancy instead of 100% redundancy. So instead of sizing one large boiler to cover your load and then having 100% backup, you can replace that boiler with, say, 2 or 3 smaller condensing boilers, and then just have one extra, 50% or 33% loaded boiler for redundancy. It also provides more operational flexibility while maintaining high efficiency. So key considerations for evaluation, which we'll go through in a little bit more detail. But generally speaking, you're looking at your system compatibility, how your distribution system is going to work with the new boilers, how your heat emitters can work with a lower operating temperature, things like that. Energy efficiency and savings, equipment and installation costs, long-term sustainability. I'm not saying this is true, but one knock on these boilers is people claim that they don't last as long. I will say, though, that it kind of seems sometimes like the age of buying a boiler and it lasting 40 years is kind of a thing of the past. Even conventional boilers, even in the same designs as maybe you bought 30 years ago, they're not made out of exactly the same materials, and they don't tend to have as long of a lifespan as they used to. But that is a knock that people say. Whether or not that's true, I'll leave to others to decide, but it's something to consider. Maintenance requirements, just like any boiler, you're considering those. Building specific considerations. One of the main things here is a lot of these boiler rooms are designed for old cast iron sectional boilers, which can basically be brought in by hand and assembled in the boiler room. There's been several opportunities where somebody's interested in a condensing boiler, and we go in and there's really no access to the room without doing significant structural modifications or architectural modifications to get the boiler into the room. These are fully assembled boilers. They're not field assembled, and you have to have some way to get in the room. A lot of times, though, these boilers do fit through the door. So you're going to size several smaller boilers. They're packaged in such a way that they might fit right through a man door. But as far as carrying it down a set of stairs or something like that, it may not be realistic. It's something that comes up quite a bit because of the nature of these old boiler rooms that may be in a basement, and that stairway is the only access to the room. So something to think about. Also payback period, obviously. I know a lot of people on this call are very aware of that type of consideration, but what is the payback on this investment? And that's certainly helped with the utility incentives that are available. So as far as your evaluation, you want to evaluate your system loads. What is your design load? What is your minimum load? What is the system turn down requirement, and as compared to the boiler turn down requirements? What is your redundancy requirement? Are you in a hospital? If you're in a school, you got to have some redundancy for reliability of the system. And you want to avoid oversizing. So oversized boilers increase boiler cycling, fuel use, wear and tear on mechanical components. And when I talk about cycling, that's basically the boiler being not able to continuously fire at the minimum load that the system requires. So it will have to turn on and off. Every time it turns on and off, there's a purge cycle. Its motor stops and starts. It's thermal stresses on the boiler. So, you want to minimize cycling as much as possible. Um, also, consider that, capacity safety factors often lead to oversizing. So you will come up with a building load. You will then apply some pickup factor to that to get to your required boiler capacity, and then that boiler capacity will fall between two manufacturer model capacities, and then you pick the next one up, and pretty quickly you're oversized by 20% on your boiler. So you want to avoid that, and maybe consider just adding an extra boiler, picking the smaller boiler, adding an extra boiler for that N+1 redundancy. And these boilers actually work pretty well together, so that's a good strategy when you're picking the sizes. I mentioned variable flow primary is going to be your recommended configuration by most manufacturers. Again, that is because you are going to get that minimum return temperature. This system is showing like in a condensing mode where you're able to turn that supply temperature down to 140 degrees and get a low return temperature to promote condensation of the flue gas in the boiler. Unfortunately, a lot of systems are already set up for primary, secondary, but those can be conducive to condensing boilers as well, and they certainly have their advantages. So this is a primary secondary system. Again, we're flowing this flow through your primary loop and then pulling off of it for your secondary loop. You want to optimize your controls to reduce the flow through this decoupler. So maybe your primary pumps and secondary pumps are communicating and kind of, I don't want to say matching flow, because you still want to kind of over pump your primary loop compared to your secondary loop, but minimizing flow through this decoupler so that you get as little blending as possible. So you can see here we have 110-degree return temperature would be great for the boilers, but we're blending with some amount of this 140-degree supply to get an actual return temperature of the boilers of 120 degrees. Still in condensing mode, but if you were to look back at that curve, decreasing your efficiency a little bit. Some other considerations, they have categories of boilers that they're low mass or high mass or mid mass. Basically, low mass boilers they have a water volume of less than 20 gallons per million BTU. So they have less thermal inertia. They require more consistent flow and are more sensitive to cycling. This is actually a benefit of the primary secondary system, is you can install these types of boilers and you can separate the flow of this loop from this loop. And so you can get that flow requirement through your primary loop. High mass boilers are where you have a water volume greater than 50 gallons per million BTU input. they have more thermal inertia, so they have better thermal stability and more flow flexibility. And so this is just something to consider when you're sizing it. You can offset the change in volume with a thermal buffer, which we'll talk about, or a buffer tank, which we'll talk about in a minute. You also want to replace single oversized boilers with multiple smaller boilers. I already mentioned that, but it improves your flexibility and redundancy. And you might want to explore dual return systems to optimize energy recovery and promote condensing in your flue gas. When I'm talking about dual return, this is the idea of that. So maybe your hot water system is you have to have that 180-degree supply temperature. You have an 160-degree return, but maybe you have some other process like a snow melt system or a pool heating system that is consistently returning colder water back to the boiler. And so even when you're not in the shoulder months of the heating season, you may be able to promote the boiler operating in condensing mode. So basically you have two returns to your boiler. You pick a lower temperature return to go, towards the outlet of your boiler to promote condensing in the flue gas. Again, we are not recommending any particular technologies for different manufacturers. I have heard the knock on this type of system that it introduces unnecessary thermal stresses in the boiler and maybe doesn't actually you have to have a pretty consistent return temperature, right, for this to happen on your alternate process. So, it's something to be evaluated. Other considerations, pump and valve modifications. You want to use VFDs on pumps greater than 5 horsepower so you can optimize your energy efficiency, adjust flow rates. You want to transition away from three-way valves to two-way valves. Again, this doesn't always happen. You can use that outdoor reset instead and kind of operate in a similar fashion you've been operating and still get some benefit out of that. But adjusting away from three-way valves where they're bypassing at the different users, it just reduces the amount of blending in your return water. We mentioned a buffer tank. So when do you need a buffer tank? Basically, a buffer tank adds volume to your system. So if you're replacing your existing boiler with a lower mass boiler, that's a good indication you need a buffer tank. If you're reducing the turn down capability of the boiler, and we'll see I'll show you in a sizing equation in a second, you'll see why that matters. Let's say you're going from a 10-to-1 turn down to a 4-to-1 turn down. That could apply. That's not as big of a point in these condensing boilers because again, often you're going to have multiple boilers. They generally have advanced controls and high turn down rates, and then your overall turn down is multiplied by the fact that you're turning down to the minimum of one of the three boilers instead of the one large boiler. Anyway, if there's indications that the system has had issues in the past with short cycling, you may need a buffer tank. If you're switching to condensing boilers, you're often reducing the volume of the boiler. So it's something you should pretty much always consider or at least evaluate. And also the buffer tanks help promote condensing operations and they help kind of buffer system spikes and it makes it easier to control your system. If the system has multiple zones, excuse me, the buffer tank smooths out demand spikes. And if the system has brief periods of high demand, it's another indication. Buffer tanks can act as your decoupler, which I mentioned as well. So you want to put it in that decoupler line on a primary secondary system. It also can be a point for air removal. So you may eliminate the need for a separate air separator. So they're, a pretty good thing to consider when you're retrofitting. The necessity of a buffer tank is basically a function of the total volume in the system. So this is the calculation for that. So your system volume requirement is based on your runtime, which is a manufacturer recommendation for the minimum amount of time between cycles on your boiler. And you multiply that by your minimum firing rate of your boiler minus your minimum anticipated system load. If you don't know your minimum anticipated system load, you can assume 0 for that number, and you'll just get a conservatively sized system volume requirement. Your tank temperature rise is basically your deadband of the boiler. So the temperature it cuts on, or the temperature it cuts off minus the temperature it cuts on. And then that'll give you your total system requirement. You subtract from that your estimated system volume, and that will give you the buffer tank size that you need. On exhaust venting, so this is a consideration with condensing boilers. You have to use Category 4 materials to prevent corrosion. You can't just pipe up to your existing flue gas system. Generally speaking, that you often are going to run a new flue gas line. So is there space to do that? Is there access to the outside at an appropriate venting location to get those new flue gas lines? It's something that you have to look at it on every installation. And it can be a challenge again with the small boiler rooms being in the basement, sometimes being in the middle of the building, that type of thing. So you have to choose proper venting design. So are you going to do a common vent or an individual vent for each boiler? The individual vent makes it much simpler from an operational standpoint, but obviously then you're having more penetrations through your wall or roof for that vent line. And then you want to choose appropriate vent termination types. So like a vent with a rain cap is not recommended. You don't want to do anything to slow down the velocity coming out of that vent. And one of the reasons why is because this is wet flue gas, right? So if you're in a cold environment, you may have some ice buildup on the exit if you use something like a rain cap, and then you're constricting the rain cap even further and exacerbating the issue, and eventually having trips on your boiler and not operating correctly. So I got to definitely check the vent termination types on these. Make sure you're picking the recommended types, as well as considering anything that's affected by wind. Like, so one of the recommendations is for the combustion air inlet, when you pipe out of the wall, you do not want something that just goes straight out. You want it to elbow down or have a T so that it's the wind doesn't blow right into it. Draft management, you want to ensure adequate draft under all operating conditions. You want to minimize excessive fittings and oversized vent diameters that can reduce draft performance. So this is particularly important if you think about just lining your existing stack for the condensing boiler flue gas outlet. That can be done, but you have to make sure that it's an appropriate diameter. So you can't just line the stack and be done with it. You got to evaluate that, and also it might have too much height and give you too much draft, and then you need to have a draft controller. As far as your combustion air intake, you do not want to. Well, there's two options. You can either use direct intake, which is where you're piping your combustion air in from the outside, or you can use room air. But what you don't want to do is combine combustion air intakes, as the boilers can kind of pull on each other and cause cross-contamination and performance issues on the air supply. So you can use a common vent for the exhaust, but you do not want to use it for the combustion air. Water chemistry and flue gas condensation management. I just want to mention the water chemistry. You want to check what the manufacturer's recommendations are and make sure that you're complying with that. As far as flue gas condensation management, we're talking about that condensate coming out of the flue gas that needs to be neutralized before you go to drain. Something to think about and something to put in your maintenance plan, if you're going to run these things. Gas pressure is, these boilers are a little bit more finicky with gas pressure. You want to maintain a consistent supply. You want to have dedicated regulators for each boiler, where, on conventional boilers, it might get away with one common regulator. These you're going to want to have one on each boiler's fuel train. And you want to keep it within a 10% drop. System redundancy, again, N+1 capacity is great. And using multiple boilers is going to be good for staging. You want to consider the reconfigurations required, which we'll talk more about. But you have control strategy, your pumping configurations, and your control valve replacements, to name a few. So speaking of controls, just kind of a high level overview of the thought process on controls, but what's going to be controlling what? So your boiler controls, again, these kind of come with more advanced controllers than in the past. So the boiler controls themselves are controlling more things than some of those components maybe were controlled by building management systems in the past. But your boiler controls are going to manage your boiler firing rates. They're going to control automatic isolation valves, which is important to make sure that you're maintaining minimum flow through your boilers. And what you want to avoid there is those nuisance trips on high temperature limit, because those usually are associated with a manual reset. So you will not be able to get the boiler back online until you go and actually press that button to manually reset the boiler. So isolation valves are a big part of that. And of course, it's easier to let the boiler control those so that it all works smoothly. Letting the boiler handle the staging so that the boilers are operating at their optimized levels. They communicate really well together. They're generally designed to be installed in a modular way so that they're operating together. And so you can let the boiler controls take care of that. And it's often pre-configured and it's more cost effective and kind of seamless integration. What is your building management system going to control? It may control the system pumps and the VSDs, although those can also be controlled by the boiler controls in many cases. It may also manage the outdoor air temperature reset, but this can also be controlled by the boiler. So generally speaking, I would say you want to let the boiler control as much as possible, but that needs to be evaluated on a case-by-case basis. Why do you want the boiler controlled staging? The advanced boiler controls improve temperature regulation, reduce cycling. The direct staging through the boiler controls eliminates the need for additional integration, so it's more cost effective. And they're more sophisticated now, so they're providing optimal performance with minimal setup. Why do the boilers sometimes have high limit issues? I mentioned that that's when your temperature gets too high, your outlet temperature. And then you require that manual reset, which is not something anybody wants. It's often because of a lack of a bypass mechanism in the system design. It could be flow imbalance across multiple boilers. It could be premature shutdown of boiler flow, so the boiler is still heating that water without flowing. It could be absence or improper use of the isolation valves, which I mentioned. And inefficient control strategies for coordinating the boilers and pumps. So all of these are kind of arguments for letting the boiler control as much as possible so that these are already kind of accounted for.
Hey Chase, we have a question in the chat. This might have been a few slides ago. It says, where can thermal storage fit well with this strategy?
The best place to install your buffer tank is in your decoupler line, and the buffer tank basically acts as your decoupler. It gives your primary loop that thermal inertia, and yeah, it's just kind of a recommended. I mean, you can make an argument to install it in other places, but that's kind of the tried and true location on a primary secondary system.
And then there's another question that says, what would be the benefit to changing out the endpoint heat exchangers, like fin tubes, to permit much lower water temperatures down to near 100 Fahrenheit? And what are the anticipated financial barriers to this as an option?
Yeah, that's a great question. So if you can change out your terminal units to A, operate at a lower supply temperature, and B, have a higher delta T across them to minimize the return temperature, that will help minimize that overall return temperature down or back to the boiler and promote being able to operate in condensing mode. I have not seen this done much in a retrofit scenario. Not a lot of people decide to go through and change out all of their unit ventilators and all their baseboard fin tubes and all these things And as far as the baseboard fin tubes go, you could possibly add uh, additional ones to just add surface area. Um, but yeah, I don't think it's commonly done to rip everything out and do it again, um, which is why you really want to use that outdoor temperature reset to try to minimize the supply temperature whenever you can. If you're doing a new installation, you could design all of your terminal units for that purpose. You could have excess surface area. They can provide the appropriate load at a lower supply temperature, get a higher delta T across the unit, uh, and then everything will work great. And you're never really having to operate outside of condensing mode. Well, theoretically. Um, but yeah, in a retrofit scenario, I don't see that done very often. But yeah, thanks for that question. Um, Considerations for retrofitting. So controls, differential pressure controls. We're talking about DP control of the system pumps. This is the most common approach for both variable primary and primary secondary systems, where you're going to control the pumps based on a DP set point. You're going to locate that transmitter at the furthest point in the system so that you're making sure that there's appropriate DP at all users. Your furthest points can be your most constraining point, right? Um, Alternatively, you can use multiple transmitters and then control to the lowest signal. Um, and you want to ensure that if your pumps are operating in parallel, that they're using the same signal for consistent operation. And you're going to want to consider a flow meter to control the system bypass to ensure that the minimum flow is met. Here's a kind of a concept of that. So this is a primary variable primary configuration. Your system pumps or your primary pumps are being controlled off of this remotely located differential pressure transmitter, but also you have this flow meter here ensuring which controls this bypass, which ensures minimum flow through the system, which can be the constraint can be the boiler or the minimum flow through the pumps. But there's usually some minimum flow requirement. Well, I guess in this case, actually, it would be the boiler because your VFD is not going to turn down below the minimum flow through the pumps. Anyway, considerations, temperature control. So on your primary secondary system, you can control to a differential temperature across the system. If you're doing a primary secondary system, you want to locate that on the secondary loop past the decoupler. If you're in a primary variable system, you want to locate it at least 5 diameters downstream of the last boiler in the system if it's multiple boilers. Maintenance. So one thing to note here, these things come in kind of fancier packaging than traditional boilers. It sometimes makes it feel like it's more of a refrigerator or a residential furnace or something where you're not typically, popping the cover yourself and doing a lot of maintenance. So don't fall into that trap. These things do require maintenance. You got to do combustion checks, checking for fuel leaks, inspecting that mesh burner, water side inspections, and verifying that your controls are operating correctly. Other considerations, ASHRAE 90.1, the 2019 version, came out with recommendations that gas boilers with capacities between 1 and 10 million BTUs per hour, which is a lot of these commercial boilers, they effectively require 90+% efficiency for new construction. So they're basically requiring condensing boilers in this standard. So that's the takeaway, is that now we're not talking about retrofits, but it is just an indication that the standards are moving in this direction where condensing boilers are going to be required in a lot of applications. Also, and I believe this is based off of that ASHRAE standard, but the Department of Energy bill has newly been adopted for water heaters and hot water boilers, which basically requires the same thing. So I think I don't have all the details here, but starting in 2026, it's going to be required that condensing boilers are going to have to be installed in a lot of applications. So I don't think that it means you can't install steam boilers anymore. And I'm sure if you don't have access to, well, I don't know how they'll manage that, but the takeaway here really is that this is becoming a requirement and eventually maybe a requirement in a lot of applications. And that is it. So any questions, please feel free to put those in the chat. And before we start losing people, I do want to mention our upcoming showcase webinar, February 18th. We have a really exciting speaker. His name is Dr. Greg Harrell. He's a senior associate at Energy Management Services and Milligan University's engineering program director. He is an instructor, author, and renowned energy systems expert with over 18 years of experience conducting industrial energy assessments across 6 continents and 26 countries. He serves as the lead technical advisor to the U.S. Department of Energy, the Industrial Program, Department of Energy Industrial Program. He developed the DOE's best practices STEAM end user training, STEAM specialist qualification training, and the STEAM system survey guide. He was also named one of the 9 global energy experts by the United Nations Industrial Development Organization. So he is an expert among experts. We're very excited to have him. I actually reference his publications from the Department of Energy, as well as he has an ASME guideline that he helped author, or maybe was the sole author of, regarding STEAM system assessments. So this is we're very excited to have him, and we hope that you guys will register for that. I actually just posted the link to register in the chat, so you can go ahead and register now. We also have a survey there. If you want to give us some feedback on topics you'd like to hear about, we'd love to hear that. As always, you can view past webinars on steammgt.com/webinars. You can also use the QR code on the bottom left to schedule a private webinar for your team. And as always, your PDH certificate, you just email me at cbean@steammgt.com, and we'll make sure to get that back to you. So all that housekeeping stuff taken care of. I am going to stick around for questions. And for anybody who wants to drop off, we really appreciate you joining us. We hope to see you next time. And we hope you have a great rest of your week.